Calc AB, I'm going to go through the true-false from the unit review, part 2. And number 9 is our first one. Now, on 9, 10, and 11, you have to be careful because if you can cancel something when you are putting these together, then you're not going to have an equality here. So let me show you what I'm talking about. So do you see how they both have the same denominator? And this, if I add my numerators over one denominator, I get that. And then I notice that I can factor a 2 out. And look, my x minus 4's cancel. And that's what my problem was, is that I was approaching 4 and I was going to get division by 0, but now that they cancel, I can see that my answer is 2. Remember that when this cancels, you're talking about having a whole, and this is actually the y value at your whole. So you have a whole at 4, 2. That means that your limit does exist. Where if you were looking back here to see if these were equivalent, this function right here, as I approach 4, this is a vertical asymptote at 4. So if I put in 4.1 to see what was happening from the right, I would get positive over positive. If I put 3.9 to see as what it was doing from the left, I would get positive over negative. So it's going from, as you approach 4 from the left, it's going to negative infinity. As you approach 4 from the right, it's going to positive infinity. Therefore, that limit does not exist. And then the same thing on this side, you're approaching a vertical asymptote. So this limit, again, is not going to exist. And so you can see that this is not true. These are not equal. So that statement was false, okay? That was a false statement there because that is not an equality. So now, the next one, we're going to look at it the same way. If we can factor and cancel something, we might have an actual answer to a limit. I mean, I didn't try, but 1 plus 6 is 7 minus 7. That's 0. So right now, I've got 0. 1 plus 5 is 6 minus 6. Right now, I have 0 divided by 0. But I'm going to try and factor. So I've got a plus 7 and a minus 1. Here, I've got a plus 6 and a minus 1. And so my x minus 1's cancel, and so that's a whole at 1. And so now if I put 1 in here, I get 8 over 7. So there is a whole on this function right here. There's a whole at the point 1 comma 8/7. Okay, but the limit exists where if you looked at these separately, you would get 0 divided by 0. And so this is not equivalent. And again, it's because you had a common factor. Okay, if you have a common factor, that's going to be what you are supposed to be looking for. All right, so let's look at this next one. Limit as x approaches 1. Now, right now, if I just go to solve this, because look, when I put 1 in, I get negative 2 here. So that makes me think, I wonder if I'm going to get 0 down here. 1 plus 2 is 3, minus 4 is negative 1. Oh my gosh, look. I actually get a value. So if you can put it in and you get a number divided by a number, then these are going to be equivalent to one another. Because it doesn't matter if I have this function and put the 1 in and get 2, or if I have this function and put the 1 in and I get negative 2, divided by, I have this function and put the 1 in and I get negative 1. See how you're getting the exact same thing? So this is true that those two limits are equivalent because there was nothing there to cancel. This bottom one was not even factorable. All right, number 12. The limit as x approaches 5 of f of x is 2. And the limit as x approaches 5 of g of x is 0. So if that's the case, then the limit as x approaches 5 of f of x divided by g of x does not exist. Okay, so let's think about that, because you know that your limit as x approaches 5 is 0, okay? So if you end up having a 0 here, like this one's 2, this one's 0, okay? So no matter what, you're going to be dividing by 0 here, and x minus 5's not canceling out. So this is going to be true for number 12, because the only way, if x minus 5 was going to cancel out, these would both be zeros, okay? So it's very similar to the next one. So let me go to the next one. I'm going to change my color again just to kind of make it. The limit as x approaches 5 of f of x is 0, and the limit as x approaches 5 of g of x is 0. If they're both 0, just like I had up here, when I said, oh, if I take the limit, I'm going to get 0 divided by 0. Remember when I said that? That was because I was approaching 1, and x minus 1 was canceling out. So if I put 1 minus 1, 1 minus 1, in both of those, I'm going to get 0. So if you're approaching one value and they're both 0, then your limit is going to actually exist. So this is going to be false, okay? Because they're saying then the limit does not exist. That should not be the case, right? Because you should be having something that cancels here, so that then it allows your limit to actually exist. Okay, does that make sense? I don't know if it does, but I hope it does. All right, so now 14. If the limit as x approaches 6 of f of x times g of x exists, then the limit must be f of 6 times g of 6. Now, hopefully you realize that that is not true. Your limit can exist, like if this is your f g of x, your limit could exist, but it actually has a value somewhere else for this f times g, or whatever, f and g could both have a value. But this is going to be false because of the fact that just because the limit exists does not mean that the function's value is that number, okay? Number 15, if p is a polynomial, then the limit as x approaches b of p of x equals p of v. Well, think about what a polynomial is, right? You've got linear, you've got quadratic, you've got cubic, you've got quartic. They're all continuous on their domain. The things that are not continuous on their domain, something like 1 over x, like a rational function, that's not a polynomial. And so, yeah, it's going to have a discontinuity. Piecewise functions could be made up of polynomial functions, but they are not polynomials. So if it is a polynomial, this should be your case. This should be a true statement if that's a polynomial, okay? 16, if the limit as x approaches 5 of f of x is infinity and the limit as x approaches 5 of g of x is infinity, then the limit as x approaches 5 of f of x minus g of x is 0. Well, if you're thinking about it and you're thinking, okay, what about infinity to minus infinity? Is that 0? This is called an indeterminate form. That means it might be 0, but it's an indeterminate form. You cannot say that this is going to be 0. This is not something that I can say, oh yeah, that's always true. No, that is not true. You could end up getting 0 after you do some things to it. You will learn either later in this class, you'll learn what the indeterminate forms are and how to work around that indeterminate form. But this would be considered false because that's an indeterminate form. Number 17, if the line x equals 1 is a vertical asymptote of y equals f of x, then f is not defined at 1. So remember what we had? We had the 1 over x with the piecewise function, and then we had a linear function. Well, this one is similar, or you could think of it as, what if you had 1 over x minus 1 and it was a piecewise function like that? And they're saying if x equals 1 is a vertical asymptote, then f is not defined at 1. Well, here's a case where I'm proving that wrong, okay? So you cannot just say that. I mean, it could be such that, it could be that it's not defined, but there is an example right here of when it would be defined. So I have to say that's false. Number 18, if f of 1 is greater than 0, so f of 1 is positive, and if f of 3 is less than 0, f of 3 is negative, then there exists a number c between 1 and 3 such that f of c is 0. Well, that would be a good thing to say. It's almost correct, except for the fact that they did not tell us that f of x was continuous. We have to say that this is false because they did not give us continuity. If they would have told us that it was going to be, that it was continuous, then we would have said, oh yes, by the intermediate value theorem, that is true. But they did not give us continuity, so therefore, we were not able to say that that is true. 19, if f is continuous at 5, and f of 5 is 2, okay, so that's the point 5 comma 2, and f of 4 is 3, so that's the point 4 comma 3, then the limit as x approaches 2 of f of 4x squared minus 11 is 2. So we have to figure out if this is true. So I'm going to solve this. I'm going to put a question mark here. We want to know if is it true. And so I'm going to say, well, the limit as x approaches 2, actually, I'm just going to put 2 in right away, sorry. And I would say f of 4 times 2 squared minus 11. F of 4 times 4 is 16 minus 11. F of 5, that is 2. Okay, so yes, that is 2. This is true. Okay, so 19, we have a true statement. 20. Now, if I put 0 in, I get 0 divided by 0. And then this is something that I asked you to memorize. I asked you to look at this and remember. I'm going to use purple just to get it to be a different color for this one. But remember, if I put in positive values like 1, 2, 3, I'm going to get positive 1. If I put in negative 1, negative 2, negative 3, I'm going to get negative 1. So you can see that at 0, your left-hand limit is negative 1, your right-hand limit is positive 1, so this is going to be does not exist, right? So that in the form that it was in was false, okay? It should have been equal to does not exist, okay? What would have been true? How could I make it true? You could have made this 0 from the right, and then that would have been a true statement, okay? All right, and then 21, if the limit as x approaches c of f of x is L, then f of c is L. Well, this is going to have to be false because you know and I know that if it is an open circle removable discontinuity, then you could have, I'm going to just put an xy axis on here. I'm going to follow this over. I'm going to say, okay, there's my L, and this is my C. So I'm approaching C from the left, I get L. I'm approaching C from the right, I get L, but yet f of C is not L, okay? So that's why I had to say, this could be true. This is possible, but it's not something that has to be true, okay? So we have to say that's false. If f is undefined at x equals c, then the limit of f of x as x approaches c does not exist. Okay, so if f is undefined at x equals c, okay, so it didn't say what kind of undefined. Could be an open circle, right? Could be something like that. So is that true then that the limit of f of x as x approaches c does not exist? No, this limit does exist here in this scenario that I just sketched. So this is going to be false. Okay, it's not always true. Okay, you could have a limit that does not exist, but you also could have a limit that existed. And here is the one example of how it could happen. Okay, so that number 22 was false. I wish I could have found the numbers of the ones that you needed, but I'm going to go ahead and stop here, and we'll go over any of the other ones for you tomorrow.